Hello everyone, welcome you all to the 12th live problem solving session for the NPTEL course titled Multirate-DSP. Myself, Saurashis Chatterjee, a PhD scholar from IIT Kanpur, and today I am going to solve a few problems with you based on the content of the lectures from week 12. Before moving on to the problems, let us briefly discuss whatever have been covered in the 12th week. So basically, the first few lectures summarizes the entire course, that is from week 1 to week 11th, the all these concepts and ideas whatever we have seen, starting from our very basic upsampling downsampling process, use of anti-aliasing filter, low pass filter, or noble identities, polyphase filter, and then comes the heart of that multirate DSP course. Those are the filter banks, like synthesis filter banks and analysis filter banks, and of course then comes the application of seeing OFDM, orthogonal frequency division multiplexing, how it fits into that multirate DSP framework, and how we can use different multirate DSP tools to improve the OFDM performance. So first few lectures, let me write it down here. First few lectures summarizes the contents, of course some important concepts, contents not all, from week 1 to week 11. In the next phase, we have seen a pretty important application of WebDM, that is quantization, and how it is basically performed at WebDM, and the benefits, and what are the criteria. Like if we do quantization, we are going to lose some kind of information in the sense, but it's also necessary because in digital domain you can only work with a finite number of values. So what is signal to quantization noise ratio, which is heart of the, like, which is the most important metric to uh, in context of quantizer, and more the signal to quantization noise ratio, the better the performance going to be. But you must also see that when we increase the number of bits in quantizer, we improve performance, but also with increasing number of bits we increase the complexity. So we kind of want a trade-off where we can more efficiently represent the data in terms of less bits using quantizer without compromising our performance. And here comes the weapons from multirate DSP. So how can we keep the performance level intact, that is with no loss of performance? How can we reduce the number of bits in quantizer? When we say that keeping performance intact, we are willing to reduce the number of bits in quantizer, what we exactly mean is that the different multirate DSP tools are going to help us in more efficient representation of data. So among them, very useful is our very own upsampling downsampling process. Let me write down here. Is sorry. Second is quantization in FDM concept. third lectures we discussed different multirate DSP tools to more efficient representation of data in context of number of bits. That basically mean reduce the bits in quantizer without loss of performance. So first way, if we have gone through the lecture, we achieve that via upsampling and corresponding, we use oversampling at the receiver side, then we quantize, then the corresponding low pass filter and downsampling. In that way we have seen the trade-off between the number of bits in quantizer and the by the way, when I say oversampling by a value of m, this m corresponds to a multiplier of the Nyquist sampling rate. So we see that by oversampling at transmitting side and corresponding downsampling at receiving side, which is inherent, we can achieve a trade-off between number of bits and number of this oversampling factor m, in a way that both increases the SQNR, signal to quantization noise ratio. So if I want a particular level of SQNR, I can trade off number of bits in a quantizer by employing higher oversampling factor. That is, in simple terms, by increasing m we can afford less number of bits b in a quantizer, or by increasing number of bits in quantizer we can afford a less oversampling factor. But since in multirate DSP context the first one seems more attractive to us, like instead of employing higher number of bits at quantizer, if we can use less number of bits in quantizer, that would be a more efficient representation of data, and we can achieve that from the multirate DSP principle of upsampling and downsampling by like employing different this by employing different oversampling factors. So this is one important method. Another one we have seen, noise sampling, sorry, use of noise shaping filter. Use of noise shaping filter. So what this noise shaping filter basically does, in a crude sense or at a very higher level, it introduces colorization in noise. Basically what happens, the quantization noise usually is uncorrelated to the input signal, but when I fed this to a noise shaping filter, I employ the noise shaping filter, what happens, you are performing coloration over this uncorrelated noise to make it correlated noise. And in that way we have seen at low frequency level we remove the quantization noise contents. However, that low frequency level the signal remain intact, therefore what happens, you can see it from this point of view, your signal remain intact at low frequency, however your quantization noise part is removed, or brought down to a very minimal level, what is going to happen? You are going to have a higher SNR. And we have seen different version of noise shaping filter, namely first order and higher order, second orders and more, which is of course more complicated. So today's problem we are going to solve mainly revolves around this quantization in OFDM part, and how we can employ different multirate DSP. Like we can use different multirate DSP has many arsenals, like many weapons in its arsenal. How can use them efficiently to facilitate the quantization in terms of reducing the number of bits in quantizer to achieve more efficient representation of data. So that is our main goal, and we are going to see that how to achieve it. So with that, let us move on to our first problem. So first problem is kind of a fill in the blanks, which says that with first order noise shaping filter, every doubling of m, which is downsampling factor, you can view it context of upsampling factor also, leads to how many bits of improvement. By the way, let me decode some of the terms here. When I say every doubling of m, m is basically a multiplier of the Nyquist rate. So yeah, like if your Nyquist frequency is like say 20 kilohertz, when every doubling of m, that is m is equal to 2, that means you are now employing 40 kilohertz. That is your oversampling, and that has been tracked by the oversampling factor m. And the bits improvement mean, the when I say improvement, it means actually less amount of bits needed. So if you have gone through the lectures, we have seen this particular SQNR expression that covers both number of bits, which is represented by capital B, and the downsampling factor m, and we have seen the relation between them. But let us go through step by step theoretically. I think it's worth revisiting, and this will also refresh your concept, so that next time you face this kind of objective problem, you can just quickly answer it down right away. So let me write here the first important thing, that goal of first order noise shaping filter is to make the noise colored and to remove the low frequency content of it. Say the goal term is not very let us see, first order noise shaping filter does that. This is known as coloration process. Okay, so let us draw the block diagram for your understanding. You have this continuous time signal xct. You are feeding this to all these are taken from lectures only. You are feeding this to a C to D converter, and you are performing sampling here. By the way, when I say sampling, I just mean over sampling by a factor of m. and here you are going to get xn, and this adder block here going to represent the quantization process. Basically what happens, you add this with some quantization noise, that's what is happening. So the uncorrelated quantization noise En in first order noise shaping filter is passed through the block with response given as 1 over z inverse, and that produces E hat of n. This is white noise. If you remember from lectures, these are the samples drawn from a wide sense stationary random process, and this is uncorrelated. That is, there is no correlation between the samples of this quantization noise from one instant to another. On the other hand, this is colored noise, and it is correlated. Why we are using the term correlated, we will see in a moment, but let us just see what happening after here. So I'm bringing a little bit down. Yeah, of course you have performed this upsampling by a factor of m, therefore you shrinks your frequency. You created actually multiple copies of frequency response. I guess you remember from the basic upsampling process, like if you have a frequency response like this, minus pi to pi, when you do some upsampling by a factor of m, what you end up doing, you create, first of all you shrink your original spectrum to minus pi by m to pi by m, and not only that, you create m minus 1 copies. M minus 1 copies. So of course you don't need that. So at the receiving end, what you need to do, you need to pass it through a low pass filter with cutoff frequency pi by m, so that you are able to capture whatever happening in this region from minus pi by m to pi by m. That is the goal, and that is also a way to restrict your spectrum to minus pi by m to pi by m, because next you will be followed with downsampling process, which is going to stretch your frequency response by factor of m. So you must see it should not go beyond pi, otherwise it's going to violate and overlap going to happen, and you obtain your the received signal xt of n, which consists of two parts, namely one is x dA of n, I am using the notations from lectures only, and another is x d of n. Now this one part here, this is your desired signal component, or you can also write signal component only, signal component, and this one here is the quantization noise component. By the way, let us see why we call it a colored noise here, because break down a relation little bit. discussion, because you have en, you are passing through this sorry, you are passing through this block 1 minus z inverse. This corresponds to your en reaching the receiver intact, and z inverse means it's a delayed version. Therefore, when I say e hat of n, you can clearly say by taking the inverse z transform, which is trivial. It is nothing but e dash of n. The new samples are nothing but the first order difference between the samples at that point, original sample uncorrelated one at that instant, minus the sample version of previous instant. So that's how it becomes correlated. This is a simply a first order difference. So it makes it dependent on the previous samples. This factorial leads to correlation, and of course that means you have colored noise, coloration of noise. So to calculate the SQNR, we need to calculate the SQNR first to see the to find the trade-off between the bits in quantizer and the oversampling factor m. So we take expected value of xdn whole square, and this is power of quantized noise component, which in lectures has been denoted as PDE, and I am writing the expression directly here because Professor David has did the elaborate calculation. That calculation procedure I think is not much help here. You can always refer to the lecture. We are just interested in the expressions and their terminologies mainly. This can be written I can write this as also like this. There's a reason I break down this multiplication into these two parts, because first part basically corresponds to the power of input quantization noise, where there is no neither is noise shaping filter nor the oversampling factor is present. I mean, when it's the this part corresponds to noise power when we do not employ any multirate-DSP tools, neither first order noise shaping filter nor oversampling factor. So in that case, our power of noise component, quantized noise component on the input side, is del square by 12. So let me just write it down here somewhere. Power of input quantization noise in absence of noise mapping, filter, and downsampling. Factor. Okay, with that we write down the necessary terminologies. First of all, we see the delta, but we have not mentioned what this is. So this is actually step size, and I will clear in a moment what step size is. M we have seen is the downsampling factor, but you need not write it. And when discussing step size, we need the XM, which is the maximum amplitude to the quantizer. Let me write it here. Maximum amplitude of quantizer. And B is the number of bits for amplitude representation. Basically, you can see this from this point of view. By the way, there is a trick here. Basically, in quantizer, when we see b plus 1 bits of quantizer, actually this 1 bit is reserved for sign representation, and the b bits are used for amplitude representation. What happens basically, if you give an input to a quantizer, quantizer has a maximum amplitude, and it divides the entire range, that is from minimum to maximum amplitude, in a certain number of levels. And how many number of levels you can incorporate, that depends on the number of bits the quantizer is going to use. Suppose the maximum amplitude is minus 16 to 16, and the quantizer has 4 bit. Therefore, how many possible different representations are possible? 2 to the power 4 in binary, correct? So there are 2 to the power 4 is 16, therefore 16 levels are possible. So you can break down the entire range minus 16 to 16 into 16 levels, where the step size is going to be 2. However, if you have a 8-bit quantizer, you can have 2 to the power 8 different representation, which means 256. Therefore you can divide the entire same range by 256. Therefore your step size decreases. It's about incorporating more granularity. We will see that in details in the upcoming problems also. I'll leave the topic as of now. So let me just briefly mention, suppose this is your range of your quantizer, which varies from minus xm to xm. You are dividing into, of course, equal length of levels, and the length of this particular step is what delta is, that is the step size. So mathematically, what is going to be the representation? Step size delta is equal to your maximum amplitude xm, your minimum is minus xm, sorry, and how many different representations are possible? 2 to the power b plus 1. By the way, this is for a b plus 1 bit quantizer. For b plus 1 bit quantizer, where 1 bit is used for sign representation, that is +1 or -1 presentation, and B bits for amplitude representation. You can see, you can further simplify this. Actually it's 2xm by 2 to the power b plus 1, which you can cancel 2 numerator and numerator, you get 2 to the power b. Okay, we need to add a new slide to progress. So let me write down what we have seen from previous slides. We have seen the power of quantization noise portion at the output as del square by 12 times pi square by 3 m cube, and we have obtained the step size as xm divided by 2 to the power b. So we replace this expression here and we obtain PDE is equal to xm square divided by 2 to the power 2b 1 over 12 pi square by 3 into 1 over m cube. Further we can bring this 2 to the power 2b over this side, and we can have here follows 1 over 12 into pi square by 3 into xm square into 1 over m cube into 1 over p dE. Next what we do, we take log base 2 on both sides, but we see we have 2b here. Here we have this log base 2 pi square by 36. I'm putting them together, just it's become unnecessary, plus log base 2 xm square by p dE. Since I am interested into the relations between the capital B and the capital M, namely the number of bits in quantizer, of course that's actually the number of bits is m plus 1, but anyway still it's the relation between the capital B and the M, that is the downsampling factor or oversampling factor, however you want to see. So since I am disregarding the rest of the terms and not simplifying them, so minus 3 log base 2 m, just remove 2 from both sides to have a better clarity. Pi square by 36, this is the constant term. This is not exactly constant, but for our example it doesn't hold much value. It's 2m. So our interest is between these two terms. Actually, I thought first to do it in context of SQNR, but later I see it's not really necessary. Even from the power of quantization noise, we can easily show the trade-off between the B and M here. So let us write it down here. Trade-off between number of bits in quantizer B and downsampling factor M. So the equation is something like this: B is equal to C minus 1.5 log M. So when M doubles, B reduces by 1.5. That means 1.5 bits of improvement. When M quadruples 4 times, B reduces by 3 bits. That corresponds to 3 bits of improvement. So basically how we are able to reach this trade-off equation from the power of quantization noise itself, because you can think it from that way. The signal power you are keeping as it is, you just consider your quantization noise power, and you see that both B and M, their goal is similar. Their goal is to reduce the quantization noise power, which in turn is going to improve the SQNR. So in Multirate-DSP framework, our goal is to use the different sampling rate, that is to increase M, so that we can reduce the number of bits in quantizer. That will lead to more efficient representation of data, and that's why the power of quantization noise is able to capture the trade-off between B and M. so that if we m doubles, we can afford to have 1.5 bits less. That would lead to 1.5 bits of improvement. Maybe you are not well understanding with fraction, so take this example. When I increase the oversampling factor by 4, that is 4 times, what happens, the number of bits we require now to achieve the same skew-NR is actually 3 bits less. That is, if we need earlier b number of bits, like for example b is equal to 8 bits of quantizer to achieve a particular skew-NR, now increasing m 4 times, we need only 8 minus 3, that is 5 bits quantizer to have similar skew-NR performance. So that would lead to more efficient representation of data. Also you can see less complexity. So you can see clearly we are using the DFT tool here, that is by increasing the oversampling or downsampling factor, however you want it to see, we are able to reduce the number of bits in quantizer, which leads to both less complexity and more efficient representation of data. So I think this is enough for theory purpose. Now let us move to our question here. It says that every doubling of m leads to how many bits of improvement. So we clearly see that every doubling of m, let me write down here, every doubling of m leads to 1.5 bits of improvement. Therefore none of the option matches here, so the fourth one is the correct answer, that is none of the above. Okay, with that let us move to our next question. That is also deals with the noise shaping filter, where yz corresponds to the z transform of output of noise shaping filter, where you have this component xz, which is the input to the noise shaping filter, and hxz corresponding transform applied on the input to noise shaping filter, and also ez corresponds to the quantization noise and its corresponding transform hz that is incorporated by the noise shaping filter, and that is given as xz plus, okay, let me write it down here. First of all, you have yz, which is x hx z xz plus h ez ez. So this is the signal component, this is quantization noise component. Where xz is the input signal fed to noise shaping filter, and ez is the quantization noise, and this is uncorrelated, by the way. So let us draw the block diagram of this uh, of the situation here. By the way, this hx and values are also given here in the term, because this is said to be xz plus 1 minus z inverse ez. So we observe that hx, okay, we'll get into that later. Let us first draw the block diagram from the lectures only. In context of noise saving filter, you are feeding this xn. I'm not showing the continuous signal and C to the converter part, because that is not relevant here, because you are not particularly employing this upsampling or downsampling factor, so no need to do that. This is an adder, and this is a block with transfer function 1 minus z inverse. This is nothing but integrator. Then you add the quantization noise here, which results into yn, and you feedback. That is why I use a adder here, but I did not say what it is. I first want to show you the output yn here. So this is nothing but a delayed version of output signal, delay block z inverse, and that adds in a negative manner, so it's a negative feedback. In the lecture there is a detailed derivation of this transfer function that we have, and I'm not going into the details. We are just interested in what we are obtaining from this. So this results into following equivalent representation given as the equivalent representation is given as follows. You have this noise en, that is being fed to this block with transfer function 1 minus z inverse. We have seen in the previous problem also that leads to coloration of the noise, and that becomes added up with the input signal here, leading to output yn. That is what because you take the z transform here, you get ez. Here you take z transform, here you get xz. Here you take z transform, you get yz. So what you are obtaining from here, yz is equal to xz plus 1 minus z inverse ez. Correct? Now what is the trick here? So we have already seen that input output response, I mean input into terms of the signal component, the hxj is 1. hxj is equal to 1, which means it has a flat response, or we can say universal response also, universal all pass filter, because if you represent it in terms of omega, you see hx e to the power j omega is equal to 1 for oh sorry, it's represent for all itself, so no need to do that. For all omega, so that means flat response across all frequency. Therefore you have to draw the spectrum. What is with the spectrum? Spectrum is something like this. It keeps going on both sides. H to the power j omega spectrum. This is 1. So that also said it allows all frequencies in input signal xz, no bias. I mean, when I say no bias, I mean it is not frequency selective. That is, it allows all the frequencies in the input signal xz in an equivalent manner. It has no particular bias towards higher frequency or lower frequency. In other terms, it's not frequency selective, so it passes all the frequencies. However, if we see the expression of h e of z, what do you see? It's 1 minus z inverse. So in terms of omega, you can write 1 minus e to the power minus j omega. When I take e to the power minus j omega by 2 common, it will become e to the power j omega by 2 minus e to the power minus j omega by 2. Correct? And this part is nothing but 2j sin omega. So you can write it as follows: e to the power minus j omega by 2j sin omega. So what is the magnitude response of this one? Magnitude response, that is, we are going to take only the amplitude of this h e to the power j omega. This exponential term, it's no role to play in magnitude response, it's 1. Similarly, j plays no role. So amplitude response becomes 2 sin omega by 2. And if I draw the spectrum, the spectrum is going to look something like this. Correct? Sine wave, sinusoidal response. Since it's omega by 2, therefore at pi it will have sin pi by 2 1. It will reach its maximum value, and we are interested in its behavior across only from minus pi to pi. So this is magnitude of h e to the power j omega. So what can be seen from this spectrum? That is frequency selective and most importantly, it removes the low frequency content. But low frequency content of whom? H is omega is multiplied with Ez, that is the quantization noise. Therefore, at output, what it does, it removes the low frequency content of quantization noise. So see, the xz, that is the input signal component, the desired signal component, that is multiplied with hxz, which has a frequency flat response, that it allows all the frequencies present in the signal, whether it is low frequency or high frequency. However, what the noise shaping filter is doing, it is making the noise colored, and therefore your effective noise response, effective noise, that output, which is the Hz times Ez, you can see that because of the nature of Hz being of sinusoid nature, it is going to remove the low frequency content of the signal multiplied with it. And what is being multiplied with He of z? Ez. Therefore, it is going to cut off or filter out the low frequency content of Ez, that is the quantization noise itself. Let me use a different term here. It filters out the low frequency content of quantization noise. So let us see which of the following statements are true. You see the first statement, this term Hz times Ez removes the low frequency portion of the quantization noise, and it is true only because we have just seen it is going to filter out the low frequency content of the quantization noise. And this next is just opposite, it boosts, therefore it's false. And signal does not lie, sorry, it should be not line, it should be lie only. Signal does not lie in the low frequency portion, and that is not true because we have seen the signal is multiplied with hxz, which is a frequency flat response across all the frequencies. It allows low frequency as well as high frequency. It has no particular bias. It doesn't cut off or filter out the low frequency portion. So signal does lie in the low frequency portion. So this is true. So therefore, what we are seeing, that first term is true, second is false, and third term is also true. I hope you understand why the third term is true, because this, as it signal xz is multiplied with hx of z, and magnitude response of hx of z allows all frequencies, therefore signal does lie in the low frequency portion. And from here we have already seen that this part removes the low frequency portion of quantization noise, so I guess we are fine. Therefore, we have seen from this question that the goal of the noise shaping filter is to remove the low frequency content of quantization noise. Now if you apply a little bit of brain here, you can see that low frequency, your signal remains as it is, however, after applying noise shaping filter. However, your low frequency content of your quantization noise are removed or mitigated to a great extent. So it is going to boost your SQNR at low frequency region. That is the goal of noise shaping filter. So let me write it down here. The noise shaping filter boosts the SQNR, especially in low frequency region. So let us move to our third question here. The third question here is relatively easy compared to the previous ones. Here we are going to use the same concept that has been discussed in the previous problems to solve. So we are mentioned a quantizer has a maximum amplitude of 12 volts, and the question is if the 8-bit quantizer is used, so what is the step size in volts. We have also seen previously the quantizer usually have a maximum amplitude, and based on the number of bits it have a certain number of levels which is it can use to represent a data particularly. Therefore, suppose you have a uh, maximum amplitude of 12 volt and you use a 2-bit quantizer, therefore you have only 2 to the power 2, that is 4 different representation. Therefore your step size in that case going to be this 12 minus of minus 12 divided by 2 to the power 2, which leads to a pretty high step size. So when you that means the granularity is reduced. So when you have larger step size, what happens, you lose the information, like because you are making a crude approximation of your input signal. Now how to avoid that? To avoid that, you can use a higher number of bits in quantizer. That would lead to more levels, and that would more accurately model your input data, continuous signal that you are feeding. That would lead to higher SQNR basically, but that comes at a cost of increased complexity and more number of bits to represent your data. So with that discussion, let me draw the basic line again here for your understanding. Suppose your quantizer have this maximum amplitude between xm to minus xm to xm, Maximum amplitude means that whatever data it gets, like quantizer cannot produce um, like sorry yeah, the idea is that whatever input data it quantizer have a maximum amplitude, and it creates certain number of levels, and when input data comes it sample it and it assign the closest uh, level it has compared to that input amplitude. That is the goal. And however, if your input signal amplitude goes beyond xm at either positive side or negative side, then the quantizer will clip it off to xm only. So in that sense you can see quantizer is not going to have a its efficient way, that quantizer cannot quantize when input signal goes beyond its maximum amplitude limit. So what quantizer going to do, it is going to divide its entire range into few levels, and among these levels, this the gap between the consecutive levels, or the length between them, is called the step size. Of course, for the similar range, if you have more number of levels, therefore your step size reduces. That leads to more accurate approximation of your data. Because suppose your input amplitude is sampled, if quantizer find it to be this value, and since this part is closest to the this level, it will assign it will do the mapping, that is this input amplitude, which is continuous amplitude, will be mapped to this discrete representation. So of course, when you increase the number of levels, you have more and more granularity, therefore your step size reduces, and you can more accurately represent your input amplitude in terms of corresponding discrete representation. So let us write down here the maximum amplitude of quantizer is equal to 12 volt, 8-bit quantizer 2 to the power 8 different representations that also mean 2 to the power n different levels. You have a maximum range that lies from x xm to minus xm, that is 2xm. Therefore your step size delta is going to be maximum range by number of levels um, 2 into 12 into 2 to the power 8, that is 24 divided by 2 to the power 8. So second option is the correct one. That was pretty easy. Let us move to our fourth question. Here you can see the quantization process is modeled as x hat of n is equal to xn plus en. If the signal x hat of n is obtained by sampling a sinusoidal signal and we are using 8 bit of quantization, what is the skew-error of the system? By the way, we are going to use uniform rounded 2's complement representation. We have seen in the lecture what does that mean. If you basically draw the graph here, it is also taken from lecture only. We have seen this staircase kind of representation. In x-axis you have the amplitude of the input continuous time signal, and you have this discrete levels here. It's being gamma, 2 delta, 3 delta, like that. So whatever input amplitude comes in this range, this has been assigned this particular value of delta, and similarly for this range it is assigned one particular value, 2 delta, and for this range 3 delta, and this onwards. This is uniform rounded 2's complement representation, uniform rounded 2's complement quantizer, of course. And 2's complement representation means you have this representation b0 up to b1 up to bb. So 2's complement representation minus b0. This part has been, this b bits has been used for amplitude representation. This part here corresponds to sign representation. So with that, let us kickstart our problem here. First of all, we write down our expression x hat of n. This is the okay, instead of writing it on the top, we can x hat of n is equal to xn plus e of n. Now this is quantization quantized signal, this is original original or unquantized signal, and this part corresponds to quantization noise. When we say that 8-bit quantizer and we use 2's complement representation, we have seen that this 8 corresponds to b plus 1 is equal to 8, that is 1, b is equal to 7. We have seen here 7 bits used for amplitude representation, 1 bit used for sign representation. Okay, so we have seen for this case I am going to use the SQNR expression directly from the lecture, because the derivation has been elaborated there on multiple occasions, so there is not much point here to discuss them. So the SQNR is obtained as 6.02b plus 10.8 minus 10 log xm square by sigma x square. Of course this is in dB. Where xm this we have seen earlier, this is nothing but the maximum amplitude, and sigma x square is the signal power variance, or in other words you can write sigma x can be standard deviation of amplitude. So for this particular question, if we see, we have already have b that is available to us. So what is that preventing us to compute SQNR value directly? You can see that is the xm and sigma x, or to be specific their ratio. Now this xm by sigma x, we have given a hint that we are sampling a sinusoidal signal. So let me write it down. we need to find xm and sigma x for sinusoidal signal. That is really the challenge for us for this particular question, because these two things are unknown. So we know xm is the maximum amplitude. So for a particular sinusoidal signal, continuous time, of course, what its representation is going to be? The xct is going to, in simplest form, is xm sin t, correct? But xm is the peak value, correct? And if I draw the continuous time representation of xct, I am drawing from minus pi to pi. This corresponds to pi by 2. This corresponds to minus pi by 2, correct? And this peak amplitude here is xm. This is minus xm. Just a minute. So we already have the xm. What is the standard deviation of the sinusoidal signal, or the sigma x square, if I willing to found? So the trick is here that sigma x is the root mean squared, that is also popularly termed as RMS value of xct, which captures its variance. And how do you compute that root mean square value? If we brush our fundamental mathematics, we obtain the root mean square value, which we now denote as sigma x square, that captures the variance of xct, or power of xct. You can see it both way. You need to basically integrate from minus pi to pi and normalize by 1 over 2 pi and x square t dt. So that is the value you need to find. Either you need to find the value of sigma x square in numerical value, or in terms of xm, so that you can have the value of ratio xm square by sigma x square. So let us see whether we are able to find it or not. I need to add a new slide here. Okay, let us start where we left, sigma x square being considered as the root mean squared value of xct, and we are going to compute it from minus pi to pi. X square t dt. So we put the value of x square t here, minus pi to pi xm square sine square t dt. Since the sine square t value is similar for minus pi to 0 to pi and minus pi to 0, we can bring a 2 outside here and integrate it from 0 to pi. We have xm square outside also, to sine square t dt. Correct. Now we take a 2 inside, so outside it becomes xm square by 2 pi, to 0 to pi 2 sine square t dt. Zero to pi, you write 2 sine square t, we can write is as 1 minus cos 2t. So we have xm squared by 2 pi. On one hand we have 0 to pi dt minus and 0 to pi cos 2t dt. Now xm square by 2 pi, here we have got pi, and here we have sine 2t by 2 from 0 to pi, and this term goes to 0. Therefore we have xm square by 2 pi into pi for xm square by 2. So we have sigma x is equal to xm by root over 2. Therefore for sinusoidal signal, xm by sigma x is given as xm by xm by root over 2, it is root over 2. So we replace xm by sigma x by root over 2 in sqnr expression in previous slide to obtain sqnr is equal to 6.02p. What else is there? Plus 10.8 plus 10.8 minus 10. Oh, sorry, I need to put a 10 here. Minus 10 log 10 square root of 2 dV. Oh, sorry, square root of 2, and this term square, sorry, it's xm by sigma x square. So therefore it becomes 6.02 into b is equal to 7. By the way, we have seen for 8-bit quantizer, the b we are concerned with, that is used for amplitude representation, is 7. That is one less. You must be careful with that. Plus 10.8 minus 10 log 10 to dV. And that results into 49.92 dV. So for this system, the SQNR comes out to be 49.92 dV. With this, let us move to our fifth question. So we have 18-bit ADC, it's 18-bit quantizer, uniform rounding and 2's complement representation of this quantizer. So we are asked to find the SQNR, assuming the ratio xm over sigma x being 4. Okay, so it's a b plus 1 bit quantizer, it's a 18-bit ADC. So in the SQNR formula we use b, that b is not 18. I need to remind you again, it's the b plus 1 is 18. That results into b being 17. Okay, and let us revisit the SQNR expression again. Write it down. 6.02b plus 10.8 minus 10 log base 10 xm square by sigma m square dV. Now in the question it is already given the ratio between xm by sigma m is equal to 4, where xm is the maximum amplitude and sigma x sigma x is the signal power, not power actually, signal standard deviation. We have seen from the previous question also. Standard deviation. So we are obtaining here 6.02 into, okay, let us keep it to b, and at the last we'll do that calculation. First simplify this rest of the part, that is 10.8 minus 20, I am bringing the square outside, log base 10 xm by sigma x. Sigma x, we obtain 6.02b plus 10 point plus 10.8 minus 20 log base 10 4 dB. The unit is essential to remember. 10.8 minus 12.04 dB. That result into 6.02 B minus 1.24 dB. Six 6.02 into 17 minus 1.24 dB, which approximately comes out to be 6.02 into 17, 101.1 dB, which is approximately can be written as 101.09 dB. So we have obtained the fourth option to be correct one. Let us move to our sixth question. Sixth question asks that in the continuation of the above question, okay, so the previous question parameters holds. We incorporate a oversampling of 16 and a corresponding downsampling in the system. So how many bits quantizer is needed to obtain similar SQNR performance? See, here basically we are employing a multirate-DSP framework of upsampling and downsampling in order to reduce the number of bits in quantizer without any performance loss, because see, we have asked that we need to have the similar SQNR performance, that is the value of SQNR we just found to be 101.09 dB, that will remain intact. So the trade-off will be basically like that we are having some oversampling, we are doing oversampling, and in that process we are uh, reducing or improving the number of bits. By that I mean reducing the number of bits in quantizer, that leads to lesser complexity and more efficient representation of data. So this is the basically bits and oversampling factor trade-off. So let me write down here, it should be oversampling factor here. So we denote as M traditionally in lectures, also in previous questions, which is the oversampling factor. So our process is like this only. We are feeding this XC2 to a C2D converter, some sampling rate, which is oversampling factor of 16. Then the quantization happens, that you can represent basically by addition of this quantization noise, and then it passes through a low pass filter that is necessary to remove the multiple copies that comes from upsampling procedure. Low pass filter is the cutoff frequency pi by m, that also acts as anti-aliasing filter for the next downsampling block. obtaining the output signal here. So actually what is happening when you I am not going to detailed discussion, you can find it in the lecture, but what is basically happening, I am giving you the brief idea as seen from diagram. Quantization noise En goes through low pass filter with cutoff frequency pi by m along with this is broken down into two parts, that is the noise component, sorry, the signal component and the quantized noise component. Down here this is signal component and this is noise component. Signal xn the power of noise component xd of n is obtained by integrating the quant noise component at receiver, the quantization noise En over a frequency range pi by m to minus pi by m to pi by m as low pass filter acts as integrator instead of minus pi to pi in cases without over sampling, and this reduces the noise power by a factor of m. Without oversampling, it is del square, which is the step size, del square by 12. But with oversampling, with oversampling, it becomes del square by 12 times 1 over m, because your range of integration is reduces by a factor of m. So does your noise power. That in turn lead to increase in SQNR, which I will show when I write the SQNR expression. So without oversampling, your integration ranges from minus pi to pi, but when you move to a oversampling zone, you have to employ this low pass filter, and low pass filter acts as the integrator. So now you have to integrate over minus pi by m to pi by m, so the integration range reduces by a factor of m. So in a way, you can think that it allows the noise component present in minus pi by m to pi by m only, compared to earlier case when it allows the noise power from minus pi by 2 to pi. That reduces the quantization noise power by a factor of m, which means it increases the SQNR by a factor of m. And in terms of dB, it is captured in the following expression, that is also you can find in lecture. It is as follows: with oversampling, the SQNR is given as 6.02. So okay, let us first denote, let us denote b1 plus 1 be the number of bits required in Quantizer. Okay, so it now becomes 6.02 times b1 plus 10.8 minus 10 log base 10 xm by sigma x whole square plus 10 log base 10 m dB, and this part is the improvement, this part is the you can say also gain from over sampling process, but your SQNR remains same. So it's not about gain in SQNR, but for the same SQNR of 1.109, we are going to have less b1 value, because now we have this non-zero and gain term that comes from oversampling process. So let us write down 6.02b plus 10.8. we have find this term, so we are not wasting time in writing it, plus 10 log 16 plus 10 log base 10 16 This leads to 6.02b being 90.3. That means the b value you are obtaining, sorry, b1 comes out to be roughly 15. That means b1 plus 1 is equal to 16 bit quantizer we need. Just be careful not to take the 15 because you obtain the b1 which is used for the amplitude representation, but there is additional 1 bit that would be used for sign representation. So your number of bits in quantizer should always be b1 plus 1, not b1 only. So you must be careful, otherwise you can make this mistake. So as we see, we have take the advantage of this oversampling process from DFT framework to reduce the number of bits in a quantizer. Now to attain the similar SQNR performance, we just need a 16-bit quantizer instead of 18-bit quantizer. So of course this is more efficient representation of data, and of course lesser complexity. That is a boon from this DFT tool of oversampling. Okay, in continuation to above system, how many bits quantizer is needed if we incorporate first order noise coloration? Okay, so we have earlier seen without sampling process we need 18-bit quantizer, then we add oversampling factor of 16 and we see that we need 16-bit quantizer. Now on top of that we are applying noise shape first order noise shaping filter. This is the making the noise colored, and intuitively you can see this is going to reduce the number of bits on quantizer further. The only question is how much reduction. So let us introduce the block diagram here, which is the similar to previous only. Let me just copy it here. Okay, it seems I cannot copy it. I don't know why I am unable to remove it. Okay, anyway, let me draw it from scratch only here. We have this input signal xct, you pass it through a C to D converter at a sampling rate with oversampling factor of 16, and this is your discrete signal you obtain xn. You need to be careful here. Instead of using uncorrelated white noise, I am first passing it through this block, simple block, but that would lead to coloration of noise. That is, instead of adding en to xn, we are adding e hat of n. That is the characteristics of first order noise shaping filter. And then the rest of the things remain same. You need to pass it through LPF with a cutoff frequency of pi by m to remove the additional copies of original spectrum. That also act as anti-aliasing filter for the next downsampling block. And at the output you are going to obtain xd of n, which you can write as a summation of two part, namely xd of n, which is the signal component and xde of n, which is the noise component. Fine. We have to maintain the similar SQNR performance. The SQNR remains fixed 101.09 dB. That is fine. Let us denote B2 plus 1 be the number of bits required in the new quantizer. Correct. So when you incorporate first order noise coloration, from the lectures we have seen that quantization noise power, we have seen in the first or second question probably, that the PDE, which is nothing but the power in the quantized noise component at the output, quantization noise component at the output, it is obtained as del square by 12 times pi square by 3 m cube. Where you can write the pi as xm by 2 to the power b, which leads to xm square by 2 to the power 2b times pi square by 12 into 1 by 3 m cube. This we obtain by replacing the step size delta as maximum amplitude xm by number of levels. Of course the number of levels is 2 to the power b plus 1, but also therefore your range is 2 times xm, so that cancels out each other, so nothing much there. And we have this signal power PDA, which is the expected value of xDAN square, is given as sigma x square. Also signal power variance of the signal power also, which is given as, we can obtain xm square by 16, as you remember here it is given that xm by sigma x is 4, as xm by sigma x is 4, that implies sigma x is xm by 4. Therefore sigma x square becomes xm square by 16. Therefore your SQNR at the output is going to be PDA by PDE. It's xm square by 16 divided by xm square by 2 to the power 2b times pi square divided by 36 m cube. This xm square cancels out each other. This is b2 anyway. Our new quantizer bit is b2 plus 1, so it's become 2 to the power 2 b2 times 12 times 3 times m cube divided by pi square into 16. So when we take sqnr in dB, what we obtain? Let us write it down. Sqnr in dB, we just take log 10 on both sides, 10 log 10, 10 log base 10 to the power 2b2 plus we sum up all these constant terms in one way, that is 36 divided by 16 pi square and plus 10 log 10 m cube. Okay, so let us take a new slide here to continue our derivation further. Okay, we have sqnr in dB, so we can write it as on the left side 101.09, on the right side we have 10 log base 10 to the power 2b2, that might come out to be 20b2 log base 10 2, so we can have here 20b2 log base 10 2 plus we have 10 log 10 10 log 10 36 by 16 pi square plus 30 log base 10 m. Log base 10 2 comes out to 3.01, 10 times log base 10 2 comes out to be 3.01, 2 times 6.02p, so I take it on the 6.02b2. On the other hand we have 101.09 minus let me calculate once 10 log base 10 36 by 16 pi square log of that times 10, okay, plus log of 16 times 30. Comes out to be 29.7. okay, that means 6.02b2 is 71.39. that implies b2 is going to be 11.86. then you can approximate to the nearest integer, that is 12. So therefore we have b2 plus, so we have the b2 to be 12. So we need a b2 plus 1 is equal to 13 bit quantizer to obtain same SQNR in presence of oversampling and first order noise coloration. Okay, so with that I conclude today's session. It is also the last session we are having, so I hope I am able to make you understand the topics in a better manner, and I really hope that this content is helpful for you understand revise the concept of multirate-DSP that has already been elaborately explained by Professor David himself. So thank you all. I am concluding this session.